Hi everybody, this is Car One. I'll be presenting with James and Albert and myself, and we'll be taking you through our project where we created a genetic algorithm to optimize an artificial neural network to drive a car. So throughout the presentation, we'll take you through about our project, features and implementation, tools and technology, and then we'll go through a demo and we'll summarize the project up. When it comes to autonomous vehicles or self-driving cars, the future is supposed to be now. But self-driving cars turned out to be harder than expected. A self-driving car is a vehicle that can operate with little to no human assistance. Self-driving cars are equipped with technologies that can create an image of their surroundings and navigate traffic. A self-driving car is also referred to as a driverless car or autonomous car. So engineers have been attempting prototypes of self-driving cars for decades. So where are we with self-driving cars? Although we still have many ways to go, many automakers in the field have made significant progress. From lane detection to assisted parking, but much of the problem requires a lot of training data. The ideal way to train a car would be to gather billions of hours of footage and train the car on that data. But gathering data is really expensive. Self-driving cars is said to revolutionize the transportation industry. In 2010, it was a great decade for AI. We saw big advancements in translation, speech generation, computer vision, object recognition, and game playing. So having self-driving cars could give a lot of people a lot more free time and increase mobility for disabled users and potentially reduce the number of road accidents. Self-driving cars can be the solution to road accidents since road accidents are 90%, since human error is not the cause of 90% of road accidents. Self-driving cars are also said to reduce emissions and cause less traffic since they're capable of keeping consistent speeds and measure between different vehicles and potentially can communicate with one another. So when it comes to autonomous vehicles, it isn't just all or nothing. There are 5 levels to self-driving cars. Level 0 would be no automation. This describes your everyday car. Level 1 is where we have driver assistance. Here is where you have your adaptive cruise control and lane keep assist. A lot of cars today offer level 1. Level 2 is partial automation. This is where it gets a little bit more complex. We have companies like Tesla's Autopilot, Volvo's Pilot Assist, and Audi's Traffic Jam Assist. And those are some examples of level 2 autonomous capabilities. Level 3 would be conditional automation. So level 3 autonomous vehicles are capable of driving themselves, but only under conditions and with limitations. Level 4 is high automation. This is where we have vehicles that can drive themselves without human interaction, but are restricted to many known use cases. Waymo has developed and is in the process of testing level 4 vehicles capable of driving themselves in most environments and road conditions. Then level 5 would be full automation. Here's where we have our true driverless car. But due to many regulations and legal battles, level 5 vehicles are still probably many years away.
In terms of our project, we created a sandbox in Unity where a user could test out a neural network and visualize what it's doing by watching a car drive around a track. This sandbox includes a car attempting to navigate a racetrack. If it hits a wall, it will stop moving and spawn a new one in the next generation. The fitness score is also recorded when it stops moving to determine the fitness and how likely it is to move on to the next generation. Over time, you'll see a car will get better at navigating over the racetrack. So the tools and technologies that we used, so our project was implemented using Unity. Unity was selected because it was a tool that we used in this class, and we also wanted to further familiarize ourselves with it. In terms of the programming language, we used C# scripts to implement our genetic algorithm and neural network. The reason that we chose C# scripts were because they were seamless to integrate with Unity, so it was the language of our choice. So as you can see here, here's our original 2D proof of concept on the upper left side. that shows our 2D track and the cars, and then our final iteration on the bottom right side where it shows the 3D cars and the 3D track. So some of the things did carry over from the 2D to 3D transition, and as you can see here, that includes the dashboard.
So the first component of our simulation was the snowy road. And this was just a snowy mountain road, which mostly composed of a road and the left and right barriers. And the barriers were just used to keep the cars within the road and detect any of the collisions. And we just download this from the Unity store where it just came with this 3D asset that somebody created. Next was our checkpoints. And we had to create these, and these are basically invisible markers spread out evenly across the course. And when a car crosses a checkpoint, they will increase their fitness score by 1. So each car which passes, or the car that passes the most checkpoints, will also be the car that has traveled the furthest and will have the highest fitness score. The track also contains sharp turns and steep hills, which introduced an interesting set of challenges that each solution had to adapt to. So if you see on the left, there's a very sharp turns on the left and the right, or where the blue arrows are. And if a car is accelerating too fast around a turn, they won't be able to successfully complete the turn. So they need to learn how to maintain their speed when doing these turns. And also on the right with the hills, these steep hills require a car to gather enough speed to successfully climb a hill. And when they are going down on the hill, they have to apply sufficient braking so they don't roll down and get too much speed. The last component was our vehicle. And we imported this vehicle from the Unity store as well, but it only contained the body and the wheels of the car and not any of the movement scripts. So we had to implement the driving mechanics to accelerate, brake, and steer this car. So if you can see on the image on the left, or I mean on the right, there are 3 proximity sensors that probe the whole environment. And these sensors explore 30 meters north, northeast, and northwest of the car and are used as input into our neural network. So how does our car actually navigate the track? So it does this using a neural network. So each neural network is actually the brain of each car. And the architecture that we settled with was a fully connected feed-forward dense neural network. And it has an input layer of 4, a hidden layer of 7, and an output layer of 4. So the input layer is all of the inputs that just go into the neural network when it's making a prediction. So as you can see, that includes the north sensor, the northeast sensor, the northwest sensor, but it also contains the speed. And in our simulation, we don't limit the speed of the car. And we noticed that the cars were able to maintain the speed because they're aware of their speed. So that goes with going down the hill, making sure they're applying the correct braking. And when they're going into a turn, making sure that they apply the correct braking as well to successfully complete the turn. So when this input is fed into a neural network, it performs a prediction by feeding the data forward through the neural network. So the information moves from the left to the right, going through the weights, being multiplied and added. And then that comes out to the output layer. And as you see, the output layer has 4 nodes, which is to accelerate, turn wheel left, turn wheel right, and brake. So what we actually do here is we take the node that had the most stimulus after the input is passed through, and that is the action that is performed. So you can just think of the neural network as a function that just maps the inputs to one of these outputs. So the goal of the genetic algorithm is to find the optimal weights and biases that will maximize the distance that the car travels. So it actually finds the weights, which are these connections between the nodes, and it also finds the biases for the neural network, which are values on the actual node. And this allows us to shift the activation functions left and right to achieve better results. This is kind of what our simulation looks like. I'll speak more about our actual genetic algorithm during the demo, which I'll just bring up here now. So here's our Unity scene that we implemented, and I'll just go into the hierarchy where you can see that we have a terrain, we have the left and the right barriers. We can zoom into these, what it kind of looks like. So it just wraps wraps across the road. You'll see it in the green. And then we also have all of our checkpoints. So let me just select all of these and zoom in. And then you can see the green checkpoints spread across the map. And this is the entirety of our map. You can see that it's fairly big in size, and there's a lot of turns, there's a lot of hills, and this is the car this is the track that the car will have to successfully complete. So now we'll just run it here, and we'll just let it run until it converges. And then Albert will just talk more about the dashboard on the top left that we implemented.
So in terms of the dashboard contents, we decided to put in the dashboard what we thought was important to keep track of for each generation or each run of our simulation and for each generation. So it contains our generation contents. So it contains what generation number we're on. So since we just started, actually we just passed one generation. So we're on the second generation now. The population size, so that is the number of cars that are initially spawned at the start for each run of the simulation. The mutation rate, the mutation radius, the current fitness, which is the highest fitness of this current generation, the max fitness, which is the highest fitness of all generations, the playback speed, which shows how fast it's running, and it could show the pause state as well. So it would be 0x if it was paused, and as well as a graph, which shows the historical fitness for each generation that we have already run.
So let's just talk more about our algorithm here while it's running. So what we do is we spawn a population of X number of cars, and at the beginning the networks are randomly initialized, so they won't make it very far. And you could see that a lot of them just start here, they drive off, some don't move at all, some move backwards, and then a lot of them just hit the wall. So none of them are really making any progress that we care about. And then afterwards, we wait until all the cars have crashed or they're not progressing. And you'll see that when they hit a wall, the proximity sensors turn off, and you have to wait until the next generation before it spawns again. Once they all crash, you'll notice the brief pause that happens, and just let this run. You'll see that brief pause that happens, and that's when we're forming the next generation. And that happens when we're forming the next generation, what we actually do is we pick the top 50 percentile, which is the top 50 best performing cars based on their fitness. And these are the ones that will move on to the next generation. And the fitness value here is just how many checkpoints they have reached. So the ones that are able to drive the car the furthest in the track are the ones who are able to make it to the next generation. And each member that is selected in the top 50 percentile will just move on to the next generation without any mutation. But they'll also create a copy of themselves, and this copy is mutated and placed in the next generation. So this copy of themselves should perform similar to how they perform, but it also have a bit of mutation, so it has the chance to even perform better than its parent. So this is a form of elitism, and we use a plus scheme because parents are being chosen, not just the children, to move on to the next generation. And then you can see that we respawn the next generation back at the starting line, and the process just keeps repeating throughout the generations. And then you'll see that we're on generation 10 right now. We also implemented a speed up ability. So we're able to, by pressing A, slow down all the way to 0, which is just then pause. And if we click S on our keyboard, we're able to speed up the simulation even more. And this is just used because running the generations takes a lot of time. So if you really want to see a conversion, you don't want to just watch the first few generations just keep hitting into the wall. You can just speed it up. I'm pretty sure you can just keep speeding this up to like unlimited, but there might be constraints placed by Unity. You see that they have a hard time trying to learn this first hill, and they all end up crashing here. But after the first hill and a couple of turns, it is usually able to complete the rest of the track without crashing. We also have 3 different camera angle, which is this bird's eye view from the right that we have. If if we click the space bar, we can get a bird's eye view from the left. And then we could also get we can also get a third person view, which is all the way up into the car. And yeah, so pretty much we'll fast forward here to when this algorithm is closer to converging. So back at the simulation, now it's getting a bit further. So you see that the current fitness now is 67. And if you look at the graph, it was stuck at around 47 to 50 for a long time. And we notice that there's three big jumps when it comes to the fitness. First, it hovers pretty low at first, where they're just trying to get over that hill, and the first couple of turns and just keep crashing. But once they're able to do that, we notice a big jump in fitness to around 50. And then it stays about 50 for a little bit. But after it's able to break through the 50 range, it's able to complete the rest of the track and get max fitness. So I'm gonna let this start running again and show you guys. So this guy made it through the first little bit, and I'll slow him down. And you could see after he finished the first half, they usually don't have trouble. And let's see if he's able to complete the rest of the track after this. And he's going through the turns. And then he's going through that turn. And you could see that they don't really keep the lanes. Like, it might look like it sometimes, but they have no concept of what a lane is, so it isn't input into the neural network. But if we were to add that, we would see some behavior that it's able to actually kind of keep the lanes, but that was out of the scope for our project. And it looks like he's about to actually complete this. So there's a big U-turn at the very end. And he's never seen this U-turn before because no car has got to this point. But as you see from the previous path that he's learned, he's able to just complete the rest. So you can see that it's able to generalize well to the rest of the track and not just overfit. And then I think he's at around 111 fitness now. And the maximum is 118. So yeah, he'll be able to convert or converge. So I'll just let it run one last time, and then we'll just point out some of the difficulties in the track and show the behavior of each of the car and how they're able to actually complete it. So you can see a lot of the cars now are actually making it further. Each car has their own type of behavior, and we see groups right here that are going really fast. And then there's also groups behind them who are going a bit slower. So they all have their own way of doing the track. And a lot of them are able to do it fast, and a lot of them are able to go slower. But at the end of the day, they're all still going to be able to eventually complete this whole track. So you see the guys who are really fast kind of crash already. And then we see the ones going a bit slower just coming along and are about to maybe complete the track. Then we see him. He gets stuck here. And these are the first group who are kind of fast. And then we see them who are going even slower through the track, just a bit more cautious. And then let's wait for the one who's able to actually complete this first turn. You're seeing a lot of them get stuck there. Okay, so here's the other one who's going a bit faster. And we notice this part right here is one of the more difficult parts in the track. So I'll just stop here and then go into first person view of this. As you can see, right here is a downward hill. And at the end of this is actually a very steep turn. So you'll see a big U-turn here. So if they don't know how to control their speed, they'll go super fast and they'll crash onto the wall. But this one is actually able to complete this one pretty good. So you see him slow down a bit and then take this turn. And then another difficult part in the map is also this turn right here. So what happens here is it's a hill, so they can't really see over top the hill to the bottom. So when they are approaching the hill, You'll see it go very slow. And on top of that, it's a very, very sharp turn. So let's see how this car is actually going to be able to navigate this one. So you'll see he takes a wide turn and he goes down the hill. And then, yeah, let's just let him run past one last time. And so this is about generation 45, and we were able to converge at generation 44. And he's just going through a track. Also, another thing to point out is the proximity sensors, when they are colliding with a wall, they show as red. And you'll see that when he's facing forward, the forward one's not hitting any barriers, so it's just green the whole time. But the ones are always colliding with the right and left barriers, so they're always red. And then, yeah, so now that it converged, we'll go back to slides where Albert will provide a last summary of the project.
So to summarize, at the start of this project, we weren't sure about how our performance would stack up with our expectations with the neural net working with the genetic algorithm, and we weren't sure if we were able to complete the track. But after implementing the neural network along with the GA tuning the weights in the 2D, our observations exceeded our initial expectations, and the performance was above expectations. And even with the transition to 3D, there weren't too many challenges in the transition, and the performance was also very good, as we saw in the previous demo. For further exploration in this topic, we think it might be interesting to maybe try out traffic, where we would have multiple cars in the lane, where you'd have to avoid that, and maybe even lane detection, which it would stay in the lane throughout the whole entire traversal of the track. And this would add further complexity and it'll be further work that we might look into doing. Thank you for watching our presentation. If you have any questions, feel free to email us. Any of our emails can be found on the D2L class list page. Thanks so much for watching.